Game 2. You're given a zero-indexed array of integers of length n. You're initially positioned at the beginning of the array. Each element in the array represents the maximum length of a forward jump from that position. In other words, if you're at position I, you can jump to position I plus whatever value is in that part of the array. And you can't jump past the end of the array, I guess. So all right. The key things that I'm noticing off the bat are the input is an array, and it's not necessarily in order, and you have to get from beginning to end. So suppose you get some input where every single cell is of of value 1. I mean, you can jump 1 forward, meaning at a minimum, we're looking at O of n time. There's no way to do better than O of n. So we'll go ahead and make that our target runtime for now. I don't see any reason why it might have to get worse than that. Let's think about O of n space. Can we beat O of n space? Probably don't need worse than that. So intuitively, this seems like it might be like maybe a dynamic programming problem where, for example, you make a table or you make another array, and each array what would it contain? It would contain, I guess, how many hops it would take to get there. So, okay, I'll talk this out. This is actually not the most optimal solution, but this is the most intuitive one, so I'm going to talk about it first. You make an array, I'm going to call it T, such that each element contains the number of hops it takes to get to that respective cell. So you start it off with 0, and all the rest you put with infinity. So I'm just going to fill it with x's. And x means infinity in this case. So let's say our input is this here. And in this case, just line these up. Kill these two. Okay. So for example, if you're starting at this first position, it takes 0 hops to get there because you start there. To get to this position, it would have to take 1, I suppose. Because, okay, so the key is you can jump up to 2 spaces from this first position. So you could jump here, and that would take you 1. So we want that to be 1, and then to get to here, this is up to 2 away from here, so that can be 1 as well, because you go straight from here to there. This one, you can't jump straight to it. So you're going to have to go through one of these intermediary cells first. And as we can see, okay, if we were to jump from here to there, that would be 2 hops, and it's the same with here. We jump from there, beginning to this position to this position, so that we're looking at 2 hops to get there. And what about this last one? This one is a little trickier. So suppose we jump from here to here to there. So we can't jump directly to the end from this middle position. So if we do our maximum jump from our first opportunity, we'll land at a spot where we end up having to do 3 hops. But if we take from a greedy perspective, if we take a suboptimal jump, so a jump that doesn't fit a greedy algorithm, and we jump only to index 0 here from this first go, we jump less than we have to. From here, we can jump 3 slots out to the end, giving us a solution of 2. So this is what we'd want our dynamic programming table to look like. Okay, so the reason this is not optimal is because you actually end up with a quadratic runtime, where for each cell, you can't just check the single maximum distance that you jump. You have to jump the maximum and intermediate values less than that, between, like 1 and 2 here, or in here you check 3, 2, 1. So you end up with, okay, that sounds like it could be potentially infinite, potentially, pseudo polynomial, since the number of steps of an inner loop would be based on the value of these cells. However, you can clip it since you're never going to jump past the end anyway, so that still makes it you're going to do up to n steps of each inner loop for an O of n outer loop, giving you quadratic time. But we can do better. We can and will do better. So instead of storing the number of hops to get to a position, if we do 2 passes through our array, and instead we store the maximum position we can get to from any particular position. So we populate that. So for example, from here, so this we can jump 2 hops, so 0, 1, 2, we can get to 2 from there. From here, we can get to, suppose that we use the amount from this, and we use its maximum jump distance. Well, that would put us at the end. So that would put us at, well, we can get to 4 from there. And what I'll illustrate next on how this approach also is better. Okay, so suppose we start here at this index 2. One that we already pointed out before, where if you somehow made it here, if you jump directly from the first index to this middle index, then you end up with having to do 3 hops to get to the end. Well, the furthest we could get from here by itself would be 0, 1, 2, 3, but that's less. So why don't we just go ahead and use the maximum distance from the previous cell? The previous cell kind of makes this one moot, but that's fine. We just use a max function, and then there you go. And then same here. This one can go, it'll go 1 over, so either way, the farthest we can get to is index 4. And then this last one doesn't matter because that's our destination, so we would stop the loop 1 early. And then in our second pass, we start from here, we jump, as far as we can. And then, so position 0, we go to index 2, so that's here. And then from here, we go to index 4, that is here. And that is our end state, and we count 2 iterations of that second pass. And that's our algorithm. So I'm going to go ahead and code that up. Okay. So first pass, vector int t, and I'm going to make it the same size as nums. And I guess I'll populate it with zeros. Doesn't super matter. This adds an O of n. Well, creating this, allocating the memory, technically is O of n time, because if you had like billions and billions of cells and some distributed system, well, you're obviously not going to do that in 1 clock cycle. So, all right, that's O of n. So then this pre-population initialization is going to be O of n, and then we'll do the first pass. So for int I equals 0, I is less than nums.size plus I. What do we do here? Let's think this through. So we want to start with first position, so we're going to have vector t of I is equal to the max of itself. Let's see. T of I is going to be the max of itself plus, all right, so the value in it plus I, since it's a number of hops forward. In the first, so if we start at index 0, then this I doesn't matter, but say we're starting at index 1, well, we can jump up to t of I positions forward from there. Or if we take the whatever, if the distance we can jump from here is not as far as what we can jump from a previous cell, we just take the distance from the previous cells, t I minus 1. And this here means that the max values will carry forward, so we don't need to check farther back than just 1 position. And actually, so, okay, if we're looking back 1, we don't care about the final one, so I'm going to change this exit condition. Yes, minus 1, and that's typo there, so let's fix that. Okay, cool. Anything else? T of I is the max of how far distance you can hop forward, or the previous value. Okay. There's our first pass. Now for our second pass. So I'm going to make a return value here. And then for int I equals let's see, do I need anything? I'm using the same variable, but different purposes here. Anyway, so int I equals 0, and then I is, our exit condition is if we are not, if we're at the last position, then we stop. So I is less than nums, wait, I and less than nums.size. And for posterity, since we're nums and t are the same size, but it's technically better juju to use the size of the array we're looping through there. So let's go ahead and do that. Max of, oh wait, no, okay. I'm actually, so nums, as a point of fixing an error, okay. The value of t of I is the max of nums of I plus I, or the previous value in t. And in this case, previous value, so we're looking back one. We don't want to start at the first index. We want to start at the next one over. And then what we want to do there is initialize our base case. I guess it is, this is dynamic programming realistically. This is still, it's just what you put in the table that makes the difference. All right, so t of 0 equals nums of 0. All right, cool. So we got our base case initialized, and we got that error fixed with using the correct variables as far as our inputs, so propagating the previous max or getting one from our input. Okay, and in the second pass, we are counting the number of steps needed to get to the end. So we start at the beginning, position 0, while we're not at the end. And then what are we doing here? So we set, at the end of each part of the loop, we want to set I equals E of I. So as a point of reference, for people who are maybe less familiar with for loop syntax in C++, this first statement is your initializer. It runs once at the beginning of the loop before anything else happens. You can declare as many variables as you want as long as it's one execution statement. And in fact, you probably could run, a function. You could use curly braces to execute multiple statements as long as one like block entity. That's what that happens. The second element or statement is your exit condition. It should yield a Boolean. In this case, when it finally comes out to false is when the loop exits. And the last statement is just, this runs after each iteration of the loop. Normally you'd use it to increment the counter variable or the index, but in this case, like, you can do whatever you want. So in this case, I am updating the index to be the value from the table that we got. And inside the loop, I want to increment our return value. Technically, since this runs one per loop, like, I could put it in there as well. I'm not going to, because even I have kind of limits on how weird I'm willing to get with these for loops and their syntax. But there you have it. So and then lastly, we wanted to return the output. Ret for return. Okay, we did this example here. I suppose I should step through the actual code as written. One thing, it's important to note, it is important to run the code as written when you do your mental example. So first runtime and then example. All right, so runtime. And as usual, my advice is to write down some of these things in comments on your code so that you are not relying on the recruiter's memory when they're doing their post-interview report. You want it to be in the code that they're going to attach, and then it's there, it's unquestionable. Yes, you covered it, you talked about it, these are your thoughts. And that's going to help you out in the long run, I think. All right, so runtime is O of n. It's 2 times O of n because you're doing 2 passes. So first one O of n loop, and then this O of n loop here. And then technically this allocation is also O of n. So these are O of n, O of n, O of n, and this is O of 1, this is O of 1. Okay, and then as far as space goes, it's also O of n space. Now, you could reuse the input. That is something that's worth asking your interviewer on. You know, if you can reuse the input space, then you can get away with O of 1 space, constant. But if you can't, then it's O of n. Either way, you're going to need an array to save these values in. So it's either O of 1 or O of n space. I'm going to call it O of n to be safe, but always bring it up. All right. Actually, that's not technically runtime, that's complexity. Okie doke. And then, do I want to do, yeah, I'll do the example as written. I'll do this one. All right, so input there. Okay. Input starts as zeros. Initialize the first one to 2. All right, 4, the first, so we start off with this index here, and then while we're not here, we are doing this. So what does this do? So we're going to set this value to the max of I, so 1 plus 3, so 4, max of 4 or 2, 4 versus 2. So 4 wins the day. And same here, you can't jump at all. All right, so it's the max of 4 previously, or 2 plus 0 is 2, so 4 versus 2. Again, that 4 wins the day. And then here it's the max of, so 0, 1, 2, 3 plus 1, so 4 versus 4. 4 wins again, doesn't matter. And then we don't care what's in this last one. So technically, I could reduce this size by 1, and maybe actually, I'll think about that. You know what, I'm going to do that. I'm going to reduce the size by 1 because I don't care. And then I don't have to check this -1 in the loop bounds here. So I'm still going through t size. And then while I is less than num's size. Yeah, okay. I think this is fine. This I will end up 1 past the end of t. But that's okay because it gets that value after the last iteration. I think that should be fine. Okay, so we put the, all right, cool. -1, index bounds, hope that works out. And okay, so that cell no longer exists, and we do our second pass. So we start off with our return value. So ret start off with 0, or int I equals 0, so start off first position, and while we are less than 0, 1, 2, 3, 4, while we're at less than 4, what do? Return plus equals 1, so we do it once for this first one, so then we jumped from 0, position 0, to position 2, and then, so we incremented, and then we did this, and then we do it again. We are going to first increment our return value, 2, and then lastly, we're going to set our index I from here to 4. It is now 4. Probably should have written these down, but anyway, index is 4. 4 is, let's see. Our exit condition is less than nums.size. Nums.size is 5. So actually, what I should do is this, I think. While I is less than t.size. So because now I is 4 and our size of t is 4. 1, 2, 3, 4. The index is as 3, the last index, but the size is 4. Okay, so that's good. That's something I caught by doing this example. I'm convinced. Let's go ahead and run it. Check for syntax. Boom. Sweet. All right, submit. No, what'd I do? Oh man, I bet it's the index bounds. Pointer, runtime reference binding to null pointer type int. Does it give me a line number? It does not. Oh, so this is not handling properly when our array size is okay. Like I can add that as a condition, as an edge case. Fair enough, touche. Okay, so if our vector size, our table would be size 0 if our input is size 1, meaning we're never going to do this first pass. Well, that would be fine. So we'd never, do we care about the first pass? I'm going to step through this actually. So if our input is 0, and then our table is Let's see, what do we do? What do we actually do? Input size, nums.size, so table is size 1, and we initialize it to 0. For int I equals 1, so this never executes. Return starts at 0. This never executes because this condition, let's see, I is less than t.size. This would actually execute the once. So maybe that's an issue. Let's see, table size is 1. I size, okay, yeah, we want it to never execute at all. So how do you get around that? I could do, I'm going to go ahead and put the edge case in. That's something to think about. I don't like doing edge cases because it could be more elegant to just handle it within the main logic itself, but it'll solve it quickly. It won't change the time complexity. I don't think recruiters ever really frown on dealing with edge cases explicitly. So if nums.size is 1, I'm going to assume the input is never of size 0, because that would be weird, because you can't jump if it's, let's see, nums size, yeah, okay, there's our constraints. The length is always at least 1. Okay, explicitly cover the edge case. First pass, second pass. There's our run. All right, let's try that again. Boom, accepted. And it is marked off. All right. You folks have a beautiful evening.